This session will give you a good idea about Fourier series analysis of continuous time signal. First of all, we should know Fourier's main contribution. He is actually Fourier. Uh, he's Fourier, and he studied vibration and heat diffusion, etc., and found series of harmonic related sinusoid to be useful in representing the temperature distribution through body. He applied the same thing and the mathematics and claimed any periodic signal could be represented by Fourier series, and also obtained a representation for a periodic signal called Fourier transform. And it has a lot of application in different field. Among these are the main one is theory of integration, point set topology, eigenfunction expansion, motion of planets, periodic behavior of earth, climate, wave in the ocean, radio and television stations, fast Fourier transform. Generally, signal system will be classified into discrete time and continuous time. Under that, we can say bounded or convergent, unbounded or convergent. It's very important to represent signals and system using different transforms. So, first of all, if the signal and system is bounded and convergent, use we may have to use Fourier transform and Fourier series. In particular, if the signal is periodic, then we have to use Fourier series technique. It may be continuous or discrete. We have to use Fourier series technique to represent the signal. At the same time, if the signal is aperiodic, under bounded and convergent, we have to use Fourier transform technique, whether it may be a continuous or a discrete time. At the same time, if the signal is said to be unbounded and non-convergent, the case of continuous time signal, we have to use Laplace transform, and if it is a discrete time signal, then we have to use Z transform. This is a small introduction about different kind of transformation and representation of signals and systems. Now we are going to discuss about Fourier series analysis. First of all, I'm going to define what is periodic signal, and then we will discuss about Fourier series technique, because Fourier series analysis are mainly used to represent periodic signal. A signal is said to be periodic if for some positive value of t, x of t should be is equal to x of t plus capital T, and for all capital T. Here, the fundamental period of x of t is the minimum positive non-zero value of capital T, for which x of t should be equal to x of t plus capital T, and also the value omega naught, that is angular frequency, which is equal to 2 pi by t, is called fundamental period. Okay. Now we are going to consider the set of harmonically related complex exponential. I'm going to call it as pi k of t, which is equal to e power j k omega naught t, which is equal to, I'm going to substitute omega is equal to 2 pi by t in this equation. I will get e power j k 2 pi by capital T into small t, and here k is equal to 0 plus or minus 1 plus or minus 2, and the series will go up to plus or minus infinity. Here all pi of k has fundamental frequency, that is multiples of omega naught is equal to 2 pi by t. So omega naught is the fundamental period. I can even say that this is first harmonic, and if it is 2 omega naught, then it is second harmonics, third harmonics, fourth harmonics, and it will go up to infinity. So each is periodic with time period capital T. Now we are going to combine all these harmonic related exponential using linear combination. So linear combination of harmonically related exponentials in the form of, I'm going to write and I'm going to call it as x of t. X of t is equal to minus infinity dash 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 and a minus 2 pi minus 2 of t, a minus 1 pi minus 1 of t, and a naught pi naught of t, and the series will go up to infinity. Here this a naught, a1, a minus 1, that is simply I can call it as a suffix k, is called Fourier series coefficient. It's actually a sum, linear combination of Fourier series coefficient and harmonic related exponential. So I'm going to write using sum of all these harmonic related exponentials. So I'm going to write this equation like sum of k is equal to minus infinity plus infinity a suffix k pi k of t. So I am going to substitute pi k of t in this equation. I will get summation k is equal to minus infinity plus infinity a suffix k e power j k omega naught t, and when you are substituting omega naught is equal to 2 pi by t, you will get this equation. Here you can find uh, a naught is the DC component, okay, and a1, a minus 1, a2, a minus 2, a3, a minus 3, something like that will go, and if k is equal to plus 1 and minus 1, then we can call it as first harmonics component, that is a fundamental component, and if k is equal to minus 2 and plus 2, then that is called second harmonics component. Okay, something like that we can say first harmonics, second harmonics, third harmonics, and it will go up to infinite. Now it's very important to know how to find this Fourier series coefficient. We have a representation, that is x of t is equal to summation k is equal to minus infinity to plus infinity e power j k omega naught t. It's very important to find out how to find Fourier series coefficient. So for that we are going to do some mathematical manipulation to exactly find out equation for Fourier series coefficient. For that I'm going to just multiply both side of this equation, the first equation, by e power j minus j n omega naught t. When I am multiplying, I will get this equation, that is x of t is equal to e power minus j n omega naught t, summation this quantity and this quantity. Now I am going to integrate both side from 0 to t. So just integrate this equation over 0 to t, I will get this. Now I'm going to consider these two exponentials. These two exponential are multiplied. I can combine this, and I can write, and also I can interchange the integration and the summation. Okay, and of course we know that k is constant, so I'm going to take outside, and I'm going to place the integration inside the summation. So when I'm combining, these are multiplied. Two exponential multiplied, I can write sum of these two exponentials. So I'm going to write this multiplication of two exponential as e power j k minus n omega naught t into dt. So first of all we have to find out the value of this integration. So this integration e power j k minus n omega naught t can be written as cos and sine, because using Euler's theorem we can write e power j theta is equal to cos theta plus j sin theta. So I'm just simply expanding this exponential as integration over 0 to t cos k minus n omega naught t plus j integration over 0 to t sin k minus n omega naught t into dt. When we are substituting k is equal to n in this equation, cos 0 you will get, at the same time here sin 0 will get, we will get. So cos 0 is 1. This term, when k is equal to 0, this term will become 1, and at the same time when we are substituting k is equal to n, this term will become 0. So this integration, I can say that when this become 1, that is cos 0 become 1, we have to integrate 0 to t 1 into dt. When you are integrating, you will get value of capital T, and that is simply I can write like some the integration value is equal to T when k is equal to n and 0 otherwise. So it means it has value when k is equal to n, and when k is not is equal to n, its value is equal to 0. Now we are going to substitute this integration in this equation. I will get, when we are substituting in this equation, I will get integration over 0 to capital T x of t into e power minus j n omega naught t, and this summation will go because we are going to substitute k is equal to n, and when we are substituting k is equal to n this equation, I'll get a suffix n, and the integration value is t. Now you can rearrange and you will get Fourier series coefficient equation. A suffix n is equal to, so I'm going to put 1 by t left hand side, 1 by t in the integration over 0 to t x of t into e power minus j omega naught t into dt, and if you are replacing k by n by k, you will get a suffix k is equal to 1 by t integration over 0 to t x of t into e power j k omega naught t into dt. So this is the formula to find out Fourier series coefficient of a given periodic signal. Based on these, we are going to define two important equations. One is synthesis equation and another one is analysis equation. Synthesis equation is used to determine the signal x of t using Fourier series coefficient a suffix k, and analysis equation is used to determine Fourier series coefficient using the signal. Okay, when we are giving signal and if they ask you to find out Fourier series coefficient, you have to use analysis equation. At the same time, if you are asked to determine the signal using Fourier series coefficient, you have to use synthesis equation. These two equations are very important equation, that is x of t is equal to summation k is equal to minus into plus infinity a suffix k e power j k omega naught t. This is very important equation. At the same time, a suffix k is equal to 1 by t integration over a single period. The single period is 0 to t, otherwise you can even treat it as minus t by 2 to plus t by 2 x of t into e power j k omega naught t into dt. But we have a special case called k is equal to 0. That is actually DC component. When you are substituting k is equal to 0 in this equation, you will get e power 0 is equal to 1. Hence, the system is reduced, this particular equation is reduced to a naught is equal to 1 by capital T integration over capital T x of t into dt, and this is actually DC or constant component of x of t. Based on this, we are going to solve few problems. First of all, we are going to determine Fourier series coefficient of the following signal x of t is equal to 1 plus sine omega naught t plus 2 cos omega naught t plus cos 2 omega naught t plus pi by 4. Now we have to use Euler's theorem to expand sine and cos waveform. So Euler's theorem says e power ix is equal to cos x plus I into sin x. At the same time, if you really want to write cos x, you can write in terms of complex exponential. That is, cos x is equal to e power ix plus e power minus ix by 2. If you want to generate sin x, you can easily generate using e power ix minus e power minus ix by 2i or 2j. So this is a way you can expand sine and cos function in terms of complex exponentials. When you are substituting this exponential expression of cos and sine, you can write this x of t like this. X of t is equal to 1, there is no change in DC component, 1 plus sine omega naught t, which can be expanded like 1 by 2j e power j omega naught t minus e power minus j omega naught t, because it's the first harmonic, and this term 2 cos omega naught t we can write like already we have 1 by 2, 1 by 2 and 2 is cancel, this term will cancel. You will get e power j omega naught t plus e power minus j omega naught t, and now we have to expand this term. So this is equal to 1 by 2 e power j 2 omega naught t plus pi by 4 plus e power minus j 2 omega naught t plus pi by 4. Now we have first harmonics and second harmonics. We have to separate first harmonics and second harmonics. That is, we have to separate e power j omega naught t, e power minus j omega naught t, and e power j 2 omega naught t, e power minus j omega 2 omega naught t. So when we are separating all these first and second harmonics, we will get x of t is equal to 1 plus 1 by 2j e power j omega naught t plus 1 minus 1 by 2j e power minus j omega naught t plus 1 by 2 e power j pi by 4 e power j 2 omega naught t plus 1 by 2 e power minus j pi by 4 e power minus j 2 omega naught t. Now this expression is used to find out Fourier series coefficient. Okay, so when we are comparing this x of t with uh, synthesis equation, we will get this constant is a naught, this one is a1, this is a minus 1, this is a2, this is a minus 2. So I have separately written all these coefficients, that is a naught is equal to 1, a1, a minus 1, a2, a minus 2, a suffix k is equal to 0. That is, so it has coefficient value only for 0, 1, minus 1, 2, minus 2, and all other coefficients are is equal to 0. That can be represented like ak is equal to 0 when magnitude of k is greater than 2. Now we have to plot this. So we have to find out magnitude of all these coefficient and plot it. Okay, we have to consider x-axis k and y-axis magnitude and plot it. For example, magnitude of a naught is 1, so this is 1, this coefficient is 1, and magnitude of a1, so magnitude you can easily find square root of real part plus real part square plus imaginary part square. So 1 square plus 1 by 2 square. So you will get when you are finding the value of this one, you will get 1.18. So a1 value is 1.18, a minus 1 value is again 1.18, a2 value is around 0.5, that you can easily find out, and a minus 2, because this is the magnitude, so you will get only positive values, so this one 0.5, and this is actually called magnitude plot of a given problem. So this problem, they have given a signal and they ask you to find out Fourier series coefficient. Now we are going to find out we are going to discuss another problem which they have given Fourier series coefficient. Using Fourier series coefficient, we are going to generate x of t. So the problem is determine x of t by assuming Fourier series coefficient given below. They have given 7 coefficient, that is a naught, a1, a minus 1, a2, a minus 2, a3, a minus 3. They have given 7 different coefficient and they are asking you to find out x of t. So we have for a synthesis equation, that is x of t is equal to, here we have only 7 coefficient and a naught, a1, a2, a3, both side, right hand side and left hand side. So the summation reduced to k is equal to minus 3 to plus 3, all our coefficients are 0, a suffix k e power j k 2 pi by t is equal to 1. Now when you are when you are trying to find out x of t, you have to substitute the coefficient value, and you have to combine harmonic related exponential, and you have to make exponential into cos and sine waveform. Here the DC component, that is a naught is equal to 1, and a1 and a minus 1 is 1 by 4. It has both first harmonic, that is j2 pi t and minus j2 pi t. um, a2 is 1 by 2, a3 is 1 by 3. So we have to combine these complex exponentials, harmonic related combination exponential, and we have to make it cos and sine waveform. Here, of course, all are added, not subtracted. Okay, hence all can be reduced into cos waveform. So x of t can be written like 1 by 2 cos 2 pi plus cos 4 pi plus 2 by 3 cos 6 pi. So this is the synthesis equation of given Fourier series coefficient. This is a simple problem.